let's imagine water flowing in a river. And this water is flowing between the land surface, so the bed of the river, and the air surface up here. And so just to be really clear in what we're talking about, I'm going to sketch some blue sky up here. And then I'm going to draw some little rocks on the riverbed. And just so you guys know, I'm going to throw in another little note right here that these riverbed particles are providing roughness. And so there are these two boundaries around this flow profile. And so right in the middle here, and I'm going to draw this in blue so we all know, this is the water. And the water is going at a velocity of about 0 at some distance at the bed or very close to the bed. That's determined by the roughness. So the reason that we know that the water is going to 0 velocity at the bed is because otherwise, if the water reached a non-zero velocity at the bed, then we'd enter a situation in which the gradient in velocity, so du over dz, would be greater than, would go to infinity, right? And that would mean that there'd be infinite shear stress, and that would completely obliterate the bed. So in order for there to be a stable situation, the flow goes to 0 at the bed, and we call this a no-slip boundary. The flow velocity is maximized at the free surface, and we often will indicate that by drawing this little skateboard at the top. And meanwhile, we'll draw this little set of hashed lines to indicate that there's a no-slip boundary, that this is attached. So this is free slip boundary. And therefore, there's no friction that occurs between the air and the water. In reality, that's not actually true. So I'm going to make a note that this is an approximation. Right? Because if you see the wind blowing across the river, you see ripples on the water, and that means that there is an interaction, there is shear. The idea here, though, is that the interaction between the air and the water is weak relative to the interaction between the bed and the water. And that is generally a pretty good approximation for rivers. And so within that flow, we have a velocity profile that looks like this. So this is just a generic curve going up. And I'm going to tell you right now that the shape of this velocity profile is roughly logarithmic. And we're going to discuss that when we get to the law of the wall. And so, over the course of the next few lectures, the roadmap is that first we're going to talk about some approximations for u bar, and this meaning the mean velocity, so averaging the velocity over the whole column. So we'll talk about the Shazy formula, Manning's formula, and maybe depending on how I situate the class for this particular term, we'll also talk about the Darcy-Weisbach formula. After that, we'll talk about formulas that actually involve a bit more physics, that are a bit less semi-empirical like these ones, and so we'll go into the into the law of the wall. And we're going to drive the law of the wall all the way back from turbulence and turbulent mixing, and so you'll see why we went through some of these earlier lectures in order to get there. Following that, we'll also look at law of the wall and see how the law of the wall might provide a mean velocity. And finally, we'll discuss bed roughness, flow velocities, and start to think about shear stresses before then we're at the point where we can start to move on to river systems and how rivers evolve over time.